In October of 2022, the Nobel Committee in Stockholm did something it almost never does. It gave the Physics Prize for a philosophical argument. Alain Aspect, John Clauser, and Anton Zeilinger stood on that stage and received the highest honor in science for proving that quantum entanglement is real. That two particles, separated by any distance, share a connection so fundamental that measuring one instantaneously determines the state of the other. Einstein had called it spooky action at a distance. Bell had written the theorem. Aspect had closed the loopholes. And in 2002, the Nobel Committee looked at 87 years of evidence, starting from the original 1935 EPR paper, and said yes. This is confirmed. Entanglement is a real feature of the universe. And you probably think that is the end of the story. You have watched the videos. You have seen the animations of two particles spinning in opposite directions. You have heard the phrase spooky action at a distance so many times it has lost all meaning. You have absorbed the standard narrative. Einstein was wrong, Bell was right, entanglement is real, and now we are building quantum computers with it. Settled science. Case closed. Move on. In the 25 years between Bell's theorem being experimentally confirmed and that Nobel ceremony, physicists discovered properties of entanglement that are so strange, so fundamentally incompatible with how any physical resource should behave, that the field has struggled to even communicate them to the public. These are not fringe results. They are published in Nature, in Science, in physical review letters. They have thousands of citations. They were produced by some of the most respected groups in quantum information theory, and they describe a version of entanglement that is nothing like the one you were taught. Entanglement can exist without being usable, permanently. You can prove it is there mathematically, unambiguously, and yet no operation in the universe can extract it. It is locked, forever. Entanglement does not combine the way any resource should. Two quantum channels, each completely useless, each with exactly zero capacity to transmit quantum information, can be combined to transmit information at a positive rate. 0 plus 0 is greater than 0. That is not a metaphor. That is a published, experimentally motivated theorem in Science magazine. Entanglement can die. Not fade, not decay exponentially like every other physical quantity in nature. It can drop from a measurable non-zero value to exactly zero at a specific, calculable moment in time, while the particles themselves are still perfectly coherent. The universe does not let entanglement fade out gracefully. It kills it. And the most devastating result of all, proven mathematically in 23 and published in Nature Physics, is that entanglement manipulation is fundamentally irreversible. If you invest entanglement to create a quantum state, you cannot get it all back. Ever. Not because of noise, not because of engineering limitations. Because the mathematics of quantum mechanics forbids it. 41.5% of your investment is permanently destroyed in a single cycle, for certain states. That number is not an approximation, it is a theorem. The 22 Nobel Prize celebrated entanglement as a confirmed phenomenon. It said nothing about any of this. And the question you should be asking is why? The answer is not conspiracy, it is not suppression, it is something more uncomfortable than that. The answer is that these results are so difficult to reconcile with the standard picture of entanglement that the field itself has not fully processed them. 27 years after the first of these properties was discovered, one of the most basic questions about it remains open. The people who should understand this best are still arguing about what it means. And the version of entanglement you were given, two particles connected across space, is not wrong exactly, but it is so incomplete that it might as well be a different phenomenon entirely. This is the story of what entanglement actually is when you look past the Nobel citation. And it starts, as these things often do, with a man who should not have survived long enough to discover any of it. Asher Perez was born Aristide Pressman on January 30th, 1934, in the village of Beaulieu-sur-Dordogne in southern France. His parents were Jewish emigrants from Lemberg, which is now Lviv in Ukraine. His father was a Polish electrical engineer who had found work in France laying power lines. The name Aristide was a compromise. His parents wanted to name him Asher after his maternal grandfather, but France maintained a list of approved given names, and Asher was not on it. So Aristide it was, at least on paper. When France fell in 1940, the family's situation deteriorated fast. Local collaborators exposed their Jewish identity to the occupation authorities. Extortion followed. His father made a decision that would determine the trajectory of modern quantum physics, though he could not have known it at the time. He joined the French resistance. His mother took 6-year-old Aristide and ran. They spent the next 4 years moving from village to village, hiding, surviving on the help of strangers, and the luck of geography. Perez would later write about this period in an autobiography he titled, "I Am the Cat Who Walks by Himself," borrowed from a Rudyard Kipling story about a creature that refuses domestication. It was, by every account, the defining metaphor of his life. The family made it to Israel in 1949. Perez's father, a practical man who had survived a war by being useful, persuaded his son to study mechanical engineering at the Technion in Haifa. There were no jobs for physicists in the young country, he argued. Physics was a luxury, engineering was survival. Perez enrolled, and then physics pulled him anyway, as it tends to do with people like him. The story that circulated at the Technion for decades afterward goes like this. As an undergraduate, Perez found a significant error in one of his professor's proofs. He pointed it out, in class, with a directness that would later make him both admired and feared in the physics community. The professor, rather than engaging with the correction, offered him a deal. He would receive the highest possible grade in the course, on one condition: he would stop attending lectures. His doctoral advisor was Nathan Rosen. Think about that for a moment. Nathan Rosen. The R in EPR, the man who, with Einstein and Podolsky, had written the 1935 paper arguing that quantum mechanics must be incomplete because entanglement seemed to require spooky instantaneous connections between distant particles. The paper that started the entire entanglement debate. Perez completed his PhD under Rosen in 1959, and the two men remained close for the rest of Rosen's life. When Rosen died, Perez asked to be buried beside him. The request was honored. Here is the irony that should unsettle you. The doctoral student of the man who co-authored the paper questioning whether entanglement was even real would go on to create the single most important mathematical tool for detecting it. And that tool would reveal something about entanglement that is, in many ways, more disturbing than anything Einstein ever worried about. In 1996, Perez published a paper in Physical Review Letters titled Separability Criterion for Density Matrices. 4 pages. Volume 77, pages 1413 through 1415. The idea was elegant in the way that only the best physics ideas are, the kind of thing that makes you wonder why nobody thought of it sooner. Here is what he proposed. Take 2 entangled particles described by their combined quantum state, written as a mathematical object called a density matrix. Now perform an operation on that matrix. Transpose the indices, but only for one of the 2 particles. Flip the matrix, but only half of it. Perez called this the partial transpose, and he showed that if the resulting matrix has any negative eigenvalue, any entry that corresponds to a negative probability, then the 2 particles must be entangled. The physical intuition behind this is remarkable, and it is the kind of thing that does not appear in the popular accounts. What Perez was doing mathematically was reversing the direction of time for just one of the two particles. If you conceptually run one particle's clock backward while leaving the other running forward, and the result is a state that cannot physically exist, a state with negative probabilities, then the two particles must be connected in a way that transcends classical correlation. They must be entangled. This test, the Perez criterion, turned out to be strictly more powerful than Bell inequality violations for detecting entanglement. There are entangled states that do not violate any Bell inequality but fail the Perez test. Entanglement, it turned out, runs deeper than Bell had measured. But the Perez criterion did something else, something Perez himself may not have fully anticipated. It created a classification system. States that fail the test, meaning their partial transpose has negative eigenvalues, are called NPT states, for negative partial transpose. States that pass the test, meaning their partial transpose remains a valid quantum state with no negative eigenvalues, are called PPT states, for positive partial transpose. For small quantum systems, two particles with two possible states each, the Perez criterion is perfect. Every entangled state fails the test. Every state that passes is genuinely unentangled. But for larger systems, particles with three or more possible states, something strange happens. There are states that pass the Perez test, states whose partial transpose has no negative eigenvalues, that are nevertheless entangled. They are entangled by every mathematical definition. They cannot be decomposed into mixtures of unentangled states. The correlation between the particles is genuinely quantum. And yet, they slip through the Perez criterion undetected. These states sit in a gap, entangled but invisible to the most powerful entanglement test available. And when three physicists in Gdansk, Poland, a father and two of his sons, looked closely at what that gap contained, they found something that would take the physics community 25 years to fully absorb. They found entanglement that is permanently, irrevocably trapped, like light behind an event horizon from which nothing can ever escape. That discovery is coming. But to understand why it shattered the field's assumptions, you first need to understand what physicists thought entanglement was good for, and why the idea that some of it could be permanently useless was not just surprising but theoretically devastating. By the mid-1990s, the quantum information community had built a compelling picture of entanglement as a resource. Think of it like fuel. You have a tank of it. It might be dirty, noisy, degraded from interactions with the environment, but you can refine it. Charles Bennett and his collaborators at IBM had shown in 1996 that noisy, imperfect entanglement could be purified through a process called distillation. Take many copies of weakly entangled pairs, apply clever sequences of local measurements and classical communication between the two parties. Throw away the failures, keep the successes. What comes out the other end is fewer pairs, but each one is cleaner, closer to the ideal maximally entangled state that quantum information theorists call a Bell state. Quantum recycling. It was beautiful, and it worked. And it made intuitive sense. If you have a noisy radio signal, you can filter it. If you have impure water, you can distill it. If you have degraded entanglement, you can purify it. The entanglement is in there, tangled up with noise, but with enough copies and enough patience, you can extract the good stuff. The underlying assumption was that entanglement is entanglement. If it exists in a quantum state, it can, at least in principle, be extracted and put to work. Teleportation, superdense coding, quantum key distribution. Whatever you need, the entanglement is there. You just have to get it out. In January of 1998, 3 members of a family in Gdansk, Poland, proved that assumption wrong. The Horodecki family is one of the most unusual collaborations in the history of physics. Ryszard Horodecki, the father, was born on September 30th, 1943. He trained originally in electronics at the University of Gdansk, then pivoted to theoretical physics and built a research group that would, over the next 3 decades, produce some of the most important results in quantum information theory. His sons grew up inside that work, not adjacent to it. Mikhail Horodecki, born in 1973, described it years later in an interview with the University of Gdansk. "My fascination comes from the family home," he said. "I was surrounded by physics in childhood. My dad is a physicist. His brother is a physicist. My cousin taught me physics at school. Dad would always demonstrate various phenomena to us, saying that it was all physics, and we were amazed. I did not even entertain the idea that you could not be a scientist." Paweł Horodecki, born in 1971, was based at the Gdansk University of Technology. Michael worked at the University of Gdansk's Institute of Theoretical Physics and Astrophysics, and later, the youngest brother, Karol, joined from the Department of Informatics. A father and 3 sons, all working on the same problem, all publishing together, all operating from a city on the Baltic coast that nobody in the mainstream physics world associated with world-changing research. Not Cambridge, not Princeton, not Caltech. Gdansk. The paper that changed everything was submitted in January 1998 and published in Physical Review Letters, Volume 80, pages 5239 through 5242. The authors were Mikhail, Paweł, and Ryszard Horodecki. The title asked a question that the field was not ready to hear. Mixed state entanglement and distillation. Is there a bound entanglement in nature? The answer was yes, and the implications were devastating. What the Horodecki showed was this: there exist quantum states that are genuinely entangled, mathematically, provably, unambiguously entangled. They cannot be decomposed into mixtures of unentangled states. The quantum correlation between the particles is real. By every formal definition of entanglement that existed in 1998, these states are entangled, but from these states no pure entanglement can ever be distilled. Not because the distillation protocol is not clever enough, not because of any practical limitation, the mathematics forbids it. The entanglement is there, but it is locked. Permanently. They called it bound entanglement. Think about what this means. You invest entanglement to create one of these states. That investment is real. It costs you something. You take clean, usable Bell pairs, and through a series of operations you produce this bound entangled state. The entanglement went in, you can prove it is still in there, but it will never come out. Not in a year, not with a better algorithm, not with infinite copies. The entanglement has crossed a one-way threshold. It has entered a region of the quantum landscape from which there is no return. The reason is connected directly to Perez's criterion. Remember the partial transpose test? The Horodeckis proved something critical about the relationship between distillation and partial transpose. If a quantum state has a positive partial transpose, if it passes the Perez test, then it cannot be distilled. Period. The proof is elegant and absolute. Distillation protocols rely on detecting the kind of quantum correlation that shows up as negative eigenvalues in the partial transpose. If those negative eigenvalues are absent, distillation has nothing to grab onto. The state is smooth in a sense. The entanglement is distributed in a way that is structurally invisible to any distillation procedure. But here is the twist that makes bound entanglement so disturbing. Paweł Horodecki, separately, constructed explicit examples of quantum states in 2x4 dimensional systems, meaning one particle with 2 possible states and another with 4 possible states that have a positive partial transpose and are nevertheless entangled. They pass the Perez test. They look to the most powerful entanglement detector available, like they might be unentangled. But they are entangled, and because they have a positive partial transpose, they cannot be distilled. These are the bound entangled states, entangled enough to not be separable, smooth enough to be undistillable, trapped in a gap that nobody had known existed. The paper that the Horodecki family had published 2 years earlier, extending Perez's criterion, had already accumulated extraordinary attention. Separability of mixed states, necessary and sufficient conditions, published in Physics Letters A in 1996, showed that the Perez test is both necessary and sufficient for detecting entanglement in the smallest possible systems, 2 by 2 and 2 by 3 dimensional spaces. That paper has been cited over 12,000 times. It is one of the most referenced papers in the entire history of quantum information theory. But its most important consequence was not the cases where the criterion works perfectly. It was the cases where it does not. The gap. The states that pass the test and are still entangled. That gap is where bound entanglement lives. You need to sit with what this means for the popular understanding of entanglement. Every video you have watched about quantum entanglement tells you the same story. 2 particles are connected. Measure one and the other responds. The connection is the point. The connection is what makes entanglement useful, what powers quantum computing. Entanglement equals connection equals resource. Bound entanglement says that is wrong, or at least it is catastrophically incomplete. Entanglement can exist as a verified mathematical fact about a quantum state and yet be completely permanently inert. It powers nothing. It enables nothing. It sits there, provably present and provably useless, like a bank account with a balance you can see but can never withdraw from. Not frozen by any authority, not restricted by any regulation. Structurally, fundamentally inaccessible. And here is the first misconception this corrects, one that matters more than you might think. You have been told entanglement is a binary property. Particles are either entangled or they are not. That is wrong. Entanglement exists on a spectrum, and that spectrum contains regions that are permanently sealed off. There is free entanglement, the kind you can distill and use. And there is bound entanglement, the kind that is locked forever. The boundary between them is not a clean line. It is a frontier that after more than 25 years of research, physicists still cannot fully map. But surely you might think this is just a mathematical curiosity, an edge case in the formalism that does not matter in practice. Something about exotic, artificially constructed quantum states that have no relevance to the real world. That argument collapsed in 2009. Elias Amselem and Mohamed Bouranein at Stockholm University created bound entangled states in the laboratory. Real, physical, photonic states. 4 qubits encoded in the polarization of photons, arranged in a configuration called the Smolin state, a well-known bound entangled state from the theoretical literature. They verified the entanglement using entanglement witnesses mathematical operators specifically designed to detect entanglement even in bound states. And they confirmed the undistillability. The entanglement was there, it could not be extracted. Published in Nature Physics, Volume 5, pages 748 through 752. A year later, Lavoie and colleagues at the University of Waterloo produced families of 4 photon-bound entangled states and published the results in Physical Review Letters, Volume 105. And in 2012, a group at the University of Electrocommunications in Tokyo achieved something even stranger. They experimentally activated bound entanglement. They showed that while bound entanglement cannot be distilled on its own, it can be used to enhance other entanglement operations, published in Physical Review Letters, Volume 109. This activation result deserves a closer look because it reveals something genuinely paradoxical about bound entanglement. The Horodeckis themselves had predicted this in 1990. in a paper titled "Bound Entanglement Can Be Activated." What they showed is that if you have a single pair of free entangled particles, usable entanglement, and you also have bound entangled states available, you can pump the bound entanglement into the free pair and boost its quality beyond what would be possible with the free pair alone. The bound entanglement cannot be distilled into pure entanglement by itself, but it can act as a kind of catalyst, enhancing operations it cannot perform alone. A dead resource that helps the living, an investment you can never recover, but that makes your other investments perform better. There is no classical analog for this. There is no thermodynamic metaphor that captures it cleanly. It is a uniquely quantum phenomenon, and it suggests that the landscape of entanglement is structured in ways that defy every intuition about how resources work. And then it got worse. In 2005, Carol Horodecki, the youngest brother, together with Michel, Powell, and Jonathan Oppenheim, proved something that should have been impossible. They showed that secure cryptographic keys, the foundation of quantum encryption, can be extracted from bound entangled states. Published in Physical Review Letters, Volume 94. Let that sit for a moment. The entanglement cannot be distilled. It cannot be purified into Bell pairs. It cannot perform teleportation. But it can generate a secure cryptographic key. Security from a resource that is, in every other operational sense, useless. The quantum world does not follow the rules you think it follows. And in 2014, Vertesi and Brunner disproved a conjecture that Asher Perez himself had made. Perez had conjectured that bound entangled states, precisely because they are so weakly entangled, could never violate a Bell inequality, that they were too feeble to display the kind of non-locality that Bell had identified as the signature of genuine quantum behavior. Published in Nature Communications Volume 5, Vertesi and Brunner showed that Perez was wrong about his own criterion's children. Bound entangled states can violate Bell inequalities. They are non-local. The states from which no pure entanglement can ever be extracted, the states that are operationally inert for distillation purposes, can still display the most fundamental signature of quantum weirdness. Bound entanglement is not a footnote. It is not an edge case. It is a permanent feature of the quantum landscape, experimentally confirmed, theoretically rich, and utterly unlike anything in classical physics. And the fact that you almost certainly have not heard of it, despite watching dozens of videos about quantum entanglement, should tell you something about how comfortable the field is communicating its own deepest results. Ryszard Horodecki, the patriarch, went on to receive the Foundation for Polish Science Prize in 2008, which is Poland's equivalent of the Nobel. He won an ERC Advanced grant in 2011, only the third person in Poland to receive one. He received the Marian Smoluchowski Medal, the highest honor of the Polish Physical Society. He directed Poland's National Center of Quantum Information Technology from 2007 to 2019, connecting 7 Polish universities into a research network, and he published 2 volumes of poetry. The man who discovered that entanglement can be permanently locked also writes verse. The first collection is titled Sum Ergo Cogito. I think, therefore I am, inverted. Existence precedes thought. For a physicist who proved that quantum states can contain realities you can verify but never access, the title is almost too perfect. The Horodecki family, all 4 of them, co-authored what remains the definitive reference on entanglement theory. Quantum Entanglement, published in Reviews of Modern Physics in 2009, volume 81, pages 865 through 942. 78 pages covering everything the field knew about entanglement at the time. A father and 3 sons writing the textbook on a phenomenon they had done more than anyone to reveal the strangeness. From a university on the Baltic coast that the mainstream physics world had never considered a powerhouse. But bound entanglement, as disturbing as it is, was only the first indication that something was deeply wrong with how physicists understood entanglement as a resource. Because while the Horodeckis were showing that entanglement could be locked, two researchers at IBM and Los Alamos were about to show something arguably worse. That entanglement does not even add up. That two quantum channels, each individually incapable of transmitting any quantum information whatsoever, each with exactly zero quantum capacity, can be combined to transmit quantum information at a positive rate. That in the quantum world, 0 plus 0 can be greater than 0, and that this is not a paradox or an error. It is a theorem to understand what physicists expected and why they expected it so confidently. In classical information theory, the theory built by Claude Shannon at Bell Labs in 1948, channel capacity is additive. If you have a communication channel that can transmit 1 bit per use and another channel that can transmit 2 bits per use, using them together gives you 3 bits per use. Always, the capacities add. This is so fundamental to Shannon's framework that it barely needs stating. It is like saying 2 plus 3 equals 5. It is just how resources combine. When quantum information theory began to mature in the late 1990s, physicists assumed the same principle would hold. A quantum channel has a certain capacity measured in qubits per use. Two channels used in parallel should have a combined capacity equal to the sum. This assumption was formalized as the minimum output entropy additivity conjecture, first stated explicitly by Christopher King and Mary Beth Ruskay in 1919. It was widely expected to be true. It felt inevitable. It was the kind of mathematical statement that most physicists filed under obviously correct, but hard to prove, a category that has a long and occasionally catastrophic history in mathematics. In 2004, Peter Shor proved something that dramatically raised the stakes. Shor was already a legend. His 1994 quantum factoring algorithm had single-handedly launched the quantum computing revolution and terrified every intelligence agency on the planet. Working at AT&T Labs, he showed that 4 seemingly independent conjectures in quantum information theory, the additivity of minimum output entropy, the additivity of Holev capacity, the additivity of entanglement of formation, and strong superadditivity of entanglement of formation were all mathematically equivalent. They would all stand or fall together. Prove one and you prove all 4. Disprove one and all 4 collapse. This should have been a warning sign. When you discover that 4 independent-looking statements are secretly the same statement, it usually means the statement is either profoundly true or profoundly false. Nature does not typically arrange for 4 different paths to lead to the same conclusion unless that conclusion is fundamental, or unless all 4 paths share a hidden flaw. On September 26, 2008, Science magazine published a paper that answered the question, not the additivity question, something stranger. Graham Smith at the IBM Thomas J. Watson Research Center and John Yard at Los Alamos National Laboratory, working on a Feynman Fellowship, demonstrated that 2 quantum channels, each with exactly 0 quantum capacity, can transmit quantum information when used together. The paper was titled Quantum Communication with Zero Capacity Channels, Volume 321, pages 1812 through 1815. Zero capacity means exactly what it sounds like. Each channel, used on its own, cannot transmit any quantum information. Not a fraction of a qubit. Not an epsilon. 0. The channel is, by every operational definition, useless for quantum communication. If you had only one of these channels, you could not send quantum information through it, no matter how many times you used it, no matter what encoding you chose, no matter how clever your error correction. It is a dead line, a brick wall. But use both channels together, and information flows. The combined capacity is strictly positive. The construction is specific and rigorous. One channel is a private Horodecki channel, which has zero quantum capacity, but positive private classical capacity. The other is a 50% erasure channel, which also has zero quantum capacity. Together, the quantum capacity of the joint channel satisfies an inequality that forces it above zero. Two brick walls placed side by side become a window. Smith described the result to journalists with a clarity that betrayed how stunned he was by his own finding. To me, the strange thing is that you have these two things that you would have thought were useless, and when you put them together, somehow there is a kind of synergy, and they develop a very quantifiable value. This does not happen when you work with classical channels. That last sentence is the key. This does not happen classically. In Shannon's theory, 0 plus 0 is 0. Always. Without exception. The additivity of capacity is built into the mathematical foundations of classical information theory at such a deep level that questioning it is like questioning whether positive numbers are positive. In the quantum world, it fails. But Smith and Yard's result was just the opening shot. 2 months earlier, Matthew Hastings at Los Alamos had posted a preprint to Archive proving something even more sweeping. Published in Nature Physics in March 2009, Volume 5, pages 255 through 257, Hastings showed that the minimum output entropy additivity conjecture itself is false. There exist quantum channels for which entangled inputs across two uses of the channel produce lower output entropy than any product input. This is more technical than the 0 plus 0 result, but its consequences are more far-reaching. Because of Shor's equivalence theorem from 2004, Hastings' result simultaneously killed all four additivity conjectures: the additivity of minimum output entropy, the additivity of whole-level capacity, the additivity of entanglement of formation, and strong superadditivity of entanglement of formation. All false. All four pillars knocked down by a single counterexample. The practical consequence is something you need to absorb slowly because it is profoundly unusual in information theory. In classical communication theory, Shannon's noisy channel coding theorem gives you a formula for the capacity of any channel. You compute a single number, the mutual information maximized over input distributions, and that number tells you the capacity. One calculation, one answer. Done. For quantum channels, no such formula exists. Because capacity is non-additive, the capacity of a quantum channel depends on how many times you use it. The capacity per use can increase as you use more copies of the channel in parallel, because entangled inputs across multiple uses can beat any strategy that treats each use independently. To compute the true capacity, you would need to optimize over infinitely many uses. Infinitely. Not 100, not 1,000. An infinite sequence, and there is no guarantee that the sequence converges at any finite point. This means that for a general quantum channel, computing its classical capacity is not merely difficult. It may be undecidable. The question, what is the capacity of this channel, may not have a computable answer. Let me say that differently. For certain quantum channels, there may be no algorithm that can compute the capacity in finite time. Shannon's elegant single-letter formula, one of the crown jewels of 20th century mathematics, has no quantum analog. Entanglement broke it. Now think about what this means in the context of the Horodecki family's bound entanglement. Section by section, the picture of entanglement as a well-behaved resource is collapsing. First, entanglement can be locked. It can exist without being extractable. Then entanglement does not add up. Two zeros make a positive. Capacities are not additive. There is no simple formula. And here is where I need you to notice the thread connecting these results. Bound entanglement is about entanglement that cannot be extracted. Non-additivity is about entanglement that creates value in combinations that should be impossible. Both results point to the same underlying reality. Entanglement has its own rules of loss and combination that have nothing to do with thermodynamics, rules that would be proven in a devastating paper 13 years later. But that proof is still ahead of us. Right now, in the timeline we're walking through, it is 2009, and the field is still reeling from Smith, Yard, and Hastings. The reaction in the quantum information community was immediate. Dave Bacon, a prominent quantum computing researcher and blogger, captured the mood. Two major additivity questions had fallen within months of each other. Multiple groups raced to produce alternative proofs and extensions. The field had known that quantum information was strange, but the non-additivity results revealed a depth of strangeness that even the specialists had not anticipated. Hastings' proof was probabilistic. He showed that channels violating additivity must exist without constructing a specific one. The proof relied on random quantum channels, random unitary matrices, and careful analysis of eigenvalue distributions in high-dimensional spaces. Finding an explicit constructible counterexample, a specific channel you could write down and say, here, this one violates additivity, remains an open problem as of 2026. Subsequent work by Belinci and Nechita in 2016 narrowed the gap, showing that violations can occur for channels with output dimensions as low as 183, and that the magnitude of the violation can approach log 2. But nobody has built a specific example you can point to and verify directly. The proof that additivity fails is certain. The proof is an existence argument. The actual counterexample remains invisible. We know it is there, we cannot find it. The quantum world is not just strange, it is evasive. The key figures in this story deserve more than footnotes, because their trajectories illuminate how quantum information theory actually works, as opposed to how the public imagines it works. Matthew Hastings received his PhD from MIT in 1997 under Leonid Levitov. He spent years at Los Alamos before becoming a partner researcher at Microsoft Research. Beyond killing the additivity conjecture, he proved the higher dimensional Lieb-Schultz-Mattis theorem, co-formulated the NLTS conjecture, which served as a precursor to the quantum PCP theorem, and developed Floquet quantum error-correcting codes. He is one of those physicists whose work you encounter every time you open a serious quantum information textbook, and whose name you almost never hear in popular science communication. Graham Smith earned his PhD at Caltech in 2006, worked at IBM Watson, moved to the University of Colorado Boulder's Giller Institute, and in 2023 joined the University of Waterloo and the Perimeter Institute. He was elected a Fellow of the American Physical Society in 2023. John Yard, who co-authored the 0+0 paper with Smith, had earned his PhD at Stanford under Thomas Cover, one of the founding figures of information theory. Yard joined the University of Waterloo and Perimeter Institute in 2016. And Peter Shaw, whose equivalence theorem had unified the four conjectures that Hastings then killed, received the ACM Turing Award in 2005. The Turing Award is the highest honor in computing, the equivalent of the Nobel in computer science. Shaw had already received the Neven-Linna Prize in 1998 and the Breakthrough Prize in Fundamental Physics in 2030. The man who showed that all four additivity conjectures were secretly the same conjecture and thereby ensured they would all die together is now one of the most honored scientists alive. But here is the thing about non-additivity that should keep you thinking long after you finish this. The Smith-Yard result and the Hastings result do not just say that quantum resources are weird. They say that quantum resources are contextual in a way that has no classical precedent. The value of a quantum channel depends on what other channels are available. The capacity of a quantum state depends on what other states you can combine it with. Nothing exists in isolation. The quantum world insists that resources be evaluated relationally, contextually, in combination. and the combinations produce outcomes that no linear theory can predict. Two zero capacity channels combining to positive capacity, bound entanglement activating free entanglement, entanglement of formation being non-additive. Over and over, the message is the same. Entanglement is not a thing, it is a relationship. And that relationship obeys rules that no classical resource theory has ever encountered. And yet, even after absorbing bound entanglement and non-additivity, you still have not heard the most viscerally disturbing discovery, because the results so far are mathematical. They are about capacities and distillation and density matrices. They live in Hilbert space, and you might be tempted to think they are artifacts of the formalism, edge cases in abstract mathematics that do not touch the physical world you inhabit. The next result obliterates that comfort. Because in 2004, 2 years before Hastings killed additivity, a physicist at the University of Rochester discovered that entanglement can die, not decay, not fade, die. At a specific calculable moment in time, the entanglement between two particles drops from a measurable quantity to exactly zero. Not asymptotically zero, not effectively zero. Mathematically, precisely, provably zero. While the particles themselves continue to exist, continue to maintain their individual quantum properties, continue to cohere, the connection between them does not weaken. It ends, abruptly, as if someone or something decided it was over. Everything in nature that decays, decays exponentially. This is not a rule of thumb. It is not an approximation. It is one of the most universal patterns in physics. Radioactive atoms decay exponentially, each nucleus having a fixed probability of decaying per unit time, producing the half-life curves that you learned about in high school chemistry. Thermal systems cool exponentially. Following Newton's law of cooling, the temperature difference between an object and its environment dropping by the same fraction in each equal time interval. A single quantum system interacting with its environment loses coherence exponentially, the off-diagonal elements of its density matrix shrinking smoothly towards zero, never quite reaching it, approaching asymptotically like a curve that gets infinitely close to the floor without ever touching it. This exponential pattern is so deeply embedded in physics that questioning it feels almost absurd. It is the signature of memoryless decay, of processes governed by constant rates, of systems that forget their history and simply evolve toward equilibrium, one smooth increment at a time. You would expect any quantum property to follow this pattern, and for individual particles it does. Entanglement does not. In 2004, Ting Yu and Joseph Henry Eberle at the University of Rochester published a paper in Physical Review Letters that should have fundamentally changed how every physicist thinks about quantum decoherence. Volume 93, Article 140404, published October 1st, 2004. The title was dry in the way that physics titles often are when the content is explosive. Finite time disentanglement via spontaneous emission. What Yu and Eberle studied was deceptively simple. Take two qubits, two quantum two-level systems, entangled with each other. Place each one in its own independent vacuum environment, separated from the other. Let them undergo spontaneous emission, the most natural and well-understood decoherence process in quantum optics. Each qubit, individually, will lose coherence exponentially. Its quantum properties will fade smoothly, asymptotically, following the textbook decay curve. This is standard physics, nothing controversial. But measure the entanglement between the two qubits as a function of time, using a quantity called Wouter's concurrence, which is the standard mathematical measure of entanglement for two qubit systems. And something happens that violates everything you have just been told about how decay works. The concurrence does not decay exponentially. It does not approach zero asymptotically. It drops to exactly zero at a finite time. A specific, calculable, non-zero moment. You and Eberle computed the exact disentanglement time for their system. It is the natural logarithm of the quantity 2 plus the square root of 2 divided by 2 multiplied by the spontaneous emission lifetime. That works out to approximately 0.54 spontaneous emission lifetimes, roughly half of one decay time. Long before the individual qubits have significantly decohered, long before their individual quantum properties have meaningfully degraded, the entanglement between them has been completely and irrecoverably annihilated. Not approximately zero, not effectively zero for practical purposes. Mathematically, exactly zero. The concurrence formula contains a maximum function, max of zero, and some expression, and the moment that expression crosses below zero, the concurrence snaps to zero and stays there. It is a non-analytic threshold, a cliff edge, a discontinuity in the behavior of a quantity that, according to everything physicists knew about decoherence, should decay smoothly. You and Eberle coined the term for this in a follow-up paper in 2006, sudden death of entanglement. The original 2004 paper accumulated over 1,270 citations and counting, and the name stuck because it captures something that the mathematics alone does not quite convey. Entanglement does not just vanish at finite time. It dies abruptly, as if there is a switch. The implications of this are more disturbing than you might initially think, and they are almost never explained properly in popular accounts. Here is what is actually happening. Two particles are entangled. Each one is interacting with its own local environment. Each one, considered in isolation, is losing quantum coherence smoothly and exponentially. If you looked at particle A alone, you would see nothing unusual. Standard exponential decay. If you looked at particle B alone, same thing. Standard, smooth, asymptotic approach toward classical behavior. But the property that connects them, the entanglement, the bipartite quantum correlation that spans the space between them, obeys a completely different rule. It does not decay smoothly. It hits a wall and vanishes. The particles are still there, their individual quantum properties are still largely intact, but the thread between them has been severed. Not frayed, severed, at a precise moment that the equations predict in advance. Here is the second misconception this corrects, and it is a big one. Every physics video you have watched tells you that quantum properties decay exponentially. They fade, they dissipate, they are eroded gradually by interactions with the environment. That is true for individual quantum systems. It is not true for entanglement between systems. Entanglement can drop to exactly zero at a finite time, not approximately zero. Exactly zero. Decoherence and disentanglement are fundamentally different processes. They follow different mathematics. They operate on different timescales. And the fact that entanglement dies faster and dies discretely rather than continuously is not a minor technical detail. It is a statement about the structure of reality. Whether entanglement sudden death occurs depends on the initial state. For 2 qubits in the state A times the 0,0 state plus B times the 1,1 state, undergoing amplitude damping, sudden death occurs when the magnitude of B exceeds the magnitude of A. These are the fragile states, the ones where the 1,1 component, the component associated with both particles being in their excited states, dominates. When A is larger than B, entanglement decays only asymptotically, following the smooth curve you would expect. These are the robust states. The universe, it seems, sorts entangled states into 2 categories: those whose connections fade and those whose connections are executed. The phenomenon extends beyond spontaneous emission. You and Eberle showed in their 2006 follow-up that classical noise, not just quantum vacuum fluctuations, can produce sudden death, phase damping, depolarizing channels, thermal environments. Across a wide range of decoherence models, entanglement sudden death appears. It is not an artifact of a particular noise model. It is a structural feature of how entanglement interacts with the environment. The man who discovered this, Joseph Henry Eberle, deserves more than the passing mention he typically gets in quantum information histories. Born in 1935, Eberle was one of the towering figures of quantum optics for 6 decades. He stood 6 feet 4 inches tall, a physical presence that matched his intellectual one. He earned his PhD from Stanford in 1962 under Edwin Thompson Jaynes, the man who, with Fred Cummings, created the Jaynes-Cummings model that describes how a single atom interacts with a single photon in a cavity. It is one of the foundational models of quantum optics, and Eberle learned the physics of light-matter interaction from the man who built its mathematical framework. Eberle spent 60 years at the University of Rochester as the Andrew Carnegie Professor of Physics. 60 years at a single institution, building a body of work that spans quantum revival phenomena, the prediction and description of diffraction-free Bessel beams, a 1987 Physical Review Letters paper with over 2,390 citations, above-threshold ionization theory, and entanglement sudden death. He founded Optics Express in 1997, making it the first open-access journal in physics, before open access was a movement or a mandate. He served as president of the Optical Society of America and received the Frederick Ives Medal, which is the highest honor in the field of optics. The personal detail that captures something essential about him. He met his wife Shirley on a blind date at a Stanford basketball game in the late 1950s. He told interviewers he got into optics by accident. His division director at the Naval Ordnance Laboratory asked him whether lasers could destroy submarines. They could not, but the question launched a career, and his connection to Nobel-winning physics runs deeper than you might expect. Donna Strickland, who won the Nobel Prize in Physics in 2018 for chirped pulse amplification, did her doctoral work at Rochester. Eberle's research on strong field ionization was part of the intellectual environment that shaped her work. Eberle died on April 30, 2025, at the age of 89. He had been teaching classes just weeks before. His total citations exceed 43,000 across more than 400 publications. Ting Yu, his collaborator on the Entanglement sudden death papers, who earned his PhD at Imperial College London and did postdoctoral work at the University of Geneva before joining Rochester, is now a professor and department chair at Stevens Institute of Technology. Their collaboration produced over a dozen joint papers on entanglement dynamics between 2002 and 2012. The experimental confirmation of entanglement sudden death came from Brazil. In 2007, a team at the Universidade Federal do Rio de Janeiro, led by M.P. Almeida and including F. de Mello, M. Hormel, A. Sales, S.P. Warborn, P.H. Souto Ribeiro, and L. Davidovich, published the results in Science, Volume 316, pages 579 through 582. April 27, 2007. They created entangled photon pairs and subjected them to controlled amplitude damping. They measured the entanglement as a function of the damping strength, and they watched it vanish. Completely. At a finite value, exactly as Yu and Eberle had predicted 3 years earlier. Each individual photon's coherence decayed smoothly. The entanglement between them died suddenly. Yu and Eberle wrote the accompanying perspective piece, The End of an Entanglement, published in the same issue of Science, page 555. The title captures the strangeness of the result better than any mathematical formula. The end, not the decay, not the reduction. The end, a discrete event, a termination. In 2008, Zbigniew Fisek at the University of Queensland and Ryszard Tanas at Adam Mickiewicz University in Poznan predicted that the reverse process also occurs. Two initially unentangled qubits, particles with no quantum correlation between them, interacting with a common environment, can become entangled after a finite time. Entanglement, sudden birth. The universe does not only kill entanglement discretely, it creates it discretely. And in some systems, both happen. Entanglement dies suddenly, there is a period of complete separability, a dark interval where no entanglement exists, and then entanglement is reborn. Suddenly, at a specific time, as if the universe turned the connection off and then, after consideration, turned it back on. You need to step back now and see the full picture that is assembling across these sections, because each result, taken alone, is disturbing but manageable. Bound entanglement is strange, but you can file it under mathematical curiosity. Non-additivity is weird, but you can tell yourself it is about abstract channel capacities. Entanglement sudden death is eerie, but you can argue it is just photons in a lab. But taken together, they say something that is very difficult to absorb. Entanglement is not a passive connection between particles. It is not a static property that persists or fades. It is a dynamic resource governed by its own laws that include permanent lockdown, non-additive combination, and discrete death. The quantum world does not merely contain entanglement, it manages it. It regulates it. It imposes rules on its creation, its extraction, its combination, and its destruction that are fundamentally different from the rules governing any other physical resource. And the deepest, most devastating of these rules had not yet been proven. The results so far, bound entanglement in 1998, sudden death in 2004, non-additivity in 2008 and 2009, all pointed toward a common conclusion: that entanglement manipulation is irreversible, that you cannot freely convert between entangled states without permanent loss, that there is an arrow to entanglement, a direction it prefers, a degradation it enforces. Physicists had hoped this arrow would turn out to be illusory, that under the right framework, the right class of operations, entanglement would prove reversible, just like thermodynamics is reversible in principle. Entropy increases in practice, but an ideal Carnot engine can, in theory, convert heat to work and back with no fundamental loss. The hope was that entanglement had its own Carnot engine, that the losses seen in bound entanglement and distillation were practical, not fundamental. In 2023, two young physicists destroyed that hope, and the number they found, the precise quantity of loss that is built into the structure of quantum mechanics itself, is one you will not forget once you hear it. To understand why the irreversibility of entanglement matters, you need to understand why physicists spent 25 years hoping it would not be true. And to understand that, you need to understand the most elegant analogy in all of quantum information theory, and why it was so seductive that an entire field built their hopes on it. In thermodynamics, there is one number that rules everything: entropy. The second law of thermodynamics says entropy never decreases in an isolated system. But the relationship between entropy and energy transformations is more subtle and more beautiful than that bare statement suggests. Two thermodynamic states with the same entropy can be connected by a reversible process. A Carnot engine, operating between a hot reservoir and a cold reservoir, can convert heat to work and work back to heat with no fundamental loss. In practice, real engines are irreversible: friction, turbulence, finite rate heat exchange. But in principle, thermodynamic transformations are reversible. The entropy function tells you everything. If you know the entropy of two states, you know whether one can be transformed into the other, and at what cost. In 1997, Sandu Popescu and Daniel Rawlich drew the analogy explicitly. For pure quantum states, states without noise, the von Neumann entropy of entanglement plays exactly the same role. If you want to convert n copies of one entangled state into m copies of another, the exchange rate in the limit of many copies is determined entirely by the ratio of their entanglement entropies. One number, one function, reversible in the asymptotic limit. The analogy with thermodynamics was not approximate, it was exact. The question that consumed the field for the next quarter century was whether this beautiful reversibility could be extended to mixed states, noisy states, realistic states, the kind of entangled states you actually encounter in nature and in the laboratory, the ones that have been degraded by interaction with the environment. For mixed states, there are two key quantities: the entanglement cost, which is how much pure entanglement you need to invest to create the state, and the distillable entanglement, which is how much pure entanglement you can recover from it. If entanglement cost equals distillable entanglement for every state, the theory is reversible. One number governs everything. The Carnot engine for entanglement exists. In 2008, Fernando Brandão and Martin Plenio appeared to prove exactly this. Published in Nature Physics, Volume 4, pages 873 through 877, with a longer mathematical version in Communications in Mathematical Physics in 2010, their result claimed that under asymptotically non-entangling operations, the regularized relative entropy of entanglement is the unique measure governing all transformations. Reversibility holds. The second law of entanglement exists. The field exhaled. The analogy with thermodynamics was saved. Entanglement had its own second law, its own entropy, its own Carnot engine. The bound entanglement problem, the non-additivity problem, the sudden death problem, all of these strange behaviors existed within a framework that was at bottom as elegant and unified as thermodynamics itself, or so it seemed. In November of 2021, Ludovico Lamy and Bartosz Regular posted a paper to the Arcsif preprint server that destroyed this picture. Published in Nature Physics, Volume 19, pages 184 through 189, on January 23, 2003, the paper carried a title that left no room for ambiguity. No second law of entanglement manipulation, after all. Lamy was Italian, born in Pisa in 1990, a gold medal winner at the Italian Physics Olympiad in 2009. He had completed his postdoc at the University of Ulm in Germany and was working at the University of Amsterdam when the paper was published. Regular was Polish, had studied mathematics at the University of Nottingham, earned his PhD there, and was working at the University of Tokyo. He described himself as a mathematician pretending to be a physicist, or vice versa. They were both in their early 30s, and they had just solved a problem that had resisted the field's best minds for a quarter century. What Lamy and Regular proved is that entanglement manipulation is fundamentally, provably, inescapably irreversible, not approximately, not in practice. Fundamentally. The entanglement cost of a quantum state can be strictly greater than its distillable entanglement, even in the asymptotic limit, even under the broadest reasonable class of operations. The Carnot engine for entanglement does not exist. The second law of entanglement is not analogous to the second law of thermodynamics. It is broken. They proved this by constructing a specific state, a 2-qubit state, they called omega-3. 2 particles, each with 3 possible states instead of 2. And for this state, the numbers are precise. The entanglement cost is exactly 1 EBIT, 1 full unit of entanglement, 1 Bell pair's worth, must be invested to create this state in the asymptotic limit. The distillable entanglement is log base 2 of 3 halves, that is approximately 0.585 EBITs. The gap is approximately 0.4158, 41.5%. That is the fraction of your investment that is permanently destroyed, not lost to noise, not dissipated by imperfect operations, destroyed by the structure of quantum mechanics itself. If you invest 7 EBITs to create 7 copies of omega-3, you can never recover more than approximately 4.1 EBITs. The remaining 2.9 EBITs are gone, permanently. They have crossed a threshold from which there is no return. Sound familiar? It should. Bound entanglement was the first hint. This is the full proof. The mathematical tool Lamy and Regular introduced to prove this is called the tempered negativity. It is a modified version of the standard negativity measure, the measure based on the Perez partial transpose that we discussed at the beginning. By carefully tempering the negativity, adding a regularization that accounts for asymptotic behavior, they produced computable lower bounds on entanglement cost that are strictly tighter than any previously known bound. These bounds are tight enough to establish the gap between cost and distillable entanglement rigorously without any assumptions or approximations. The result is devastating in its generality. It holds for all non-entangling operations the broadest reasonable class of quantum operations. It persists even when small amounts of entanglement generation are allowed as overhead. It cannot be circumvented by tolerating small errors in the output states. And it extends to quantum channels as well as quantum states, meaning the irreversibility is not limited to static resources, but applies to dynamic processes as well. Lamy described the significance with a precision that reflects his mathematical training. Using entangling operations would be like running a distillery in which alcohol from elsewhere is secretly added to the beverage, he said. You cannot cheat your way to reversibility by smuggling in extra entanglement. The irreversibility is structural. It is built into the fabric. And then, in a twist that would be unbelievable in fiction, the proof that entanglement was reversible, the Brandau-Plenio result from 2008, was found to contain a fatal error. In May of 2022, a team that included Berta, Brandau himself, Gur, Lamy, Plenio, Regular, and Thomas Michel identified a gap in lemma 3. 9 of the 2010 paper, the proof had relied on a generalized version of the quantum Stein's lemma, and that generalization turned out to be unjustified. The result was published in the journal Quantum, Volume 7, page 1103, in 2023. Think about the timeline. For 13 years, from 2008 to 2001, the field believed entanglement was reversible. This belief was based on a published proof in Nature Physics, extended and detailed in Communications in Mathematical Physics. It was cited hundreds of times. It shaped the direction of research programs. It influenced how people thought about the foundations of quantum information. And it was wrong. Not slightly wrong, not wrong in a technical detail that does not affect the main conclusion. Wrong in a way that invalidated this central claim. Lamy and Regular had proven irreversibility independently, before the gap in Brandau-Plenio was formally identified. Their proof stands on its own foundations. It does not depend on the failure of the earlier result, but the timing is striking. The field spent 13 years building on a result that was not true, and it took 2 early career researchers, one Italian and one Polish, working outside the established centers of quantum information theory to set the record straight. Lamy went on to win an ERC starting grant in 2204, approximately €1.5 million, to pursue what he titled Entanglement Theory, a Quantum Odyssey at the Scuola Normale Superiore in Pisa. Regular became a Riken Hakubi team leader in Japan. Both are still in their mid-30s. The problem they solved had defeated the field for 25 years. But the story did not end with the proof, because in July of 2025, a different group of physicists published a result that at first glance appeared to contradict everything Lamy and Regula had shown, and the fact that it does not contradict it, that both results are simultaneously true, tells you something about entanglement that is perhaps the most unsettling lesson of all. Ray Gennady, Tulje Varun Kondra, Nelly Eng and Alexander Streltsov published a paper in Physical Review Letters, Volume 135, Article 010202. The title was Second Law of Entanglement Manipulation with an Entanglement Battery. And their result was this: if you allow an auxiliary quantum system, a battery, to participate in the entanglement transformation, storing and supplying entanglement as needed, and if you require only that the battery returns to its original state at the end of the process, with no net loss or gain, then entanglement transformations become reversible. The second law is recovered. The Carnot engine exists, but only with the battery. This sounds like a loophole. It sounds like Lamy and Regula proved irreversibility, and then someone found a way around it. But that is not what happened. What happened is subtler and more important. Lamy and Regula proved that under LOCC, local operations and classical communication, the standard framework for entanglement manipulation, irreversibility is fundamental. The 41.5% loss for omega-3 is real and inescapable within that framework. Gennady and colleagues showed that if you expand the framework, if you add a battery that can lend and reclaim entanglement without net cost, reversibility returns. The analogy is precise and illuminating. Imagine you have a factory that converts one type of fuel into another. Lamy and Regula proved that this factory, operating with only its own internal resources, permanently wastes 41.5% of the fuel in every conversion cycle. Gennady and colleagues proved that if you give the factory access to an external fuel reserve, a battery that loans fuel during the conversion and takes it back afterward, with no net expenditure, then the factory can operate without waste. The battery does not add fuel. It does not create something from nothing. It provides a scaffold, a temporary support structure that allows the conversion to proceed without loss. Both results are true, both are proven, and together they reveal something about entanglement that no single result captures alone. The irreversibility is real but contextual. It depends on the resources available. Under standard operations, entanglement has an arrow. Loss is permanent, but if you have access to auxiliary entanglement, that arrow can be reversed. The rules of the game change depending on what you bring to the table. This is profoundly unlike thermodynamics. In thermodynamics, the second law holds regardless of what auxiliary systems you have. You cannot make a perpetual motion machine by adding a battery. The arrow of entropy is universal. The arrow of entanglement is not. It is real within a framework and absent within another. The universe imposes irreversibility on entanglement, but the strictness of that imposition depends on the resources available. Entanglement's laws are conditional in a way that thermodynamic laws are not. And this conditionality connects directly back to the non-additivity results from 2008. Remember Smith and Yard? Two zero-capacity channels combining to positive capacity. The value of a quantum resource depends on what other resources are present. Non-additivity and framework-dependent irreversibility are two faces of the same deep truth. Entanglement is relational. Its properties, its value, its very behavior depends on context, on combination, on what else exists alongside it. There is no view from nowhere. There is no absolute measure of entanglement's usefulness or behavior. Everything depends on everything else. Lamy himself acknowledged the complexity of the situation. In April of 2024, he and Regula published a follow-up in Nature Communications, Volume 15, showing that if you allow probabilistic protocols, transformations that may fail but succeed with a probability bounded away from zero, then reversibility can also be recovered. Under these conditions, the regularized relative entropy of entanglement becomes the unique operational measure, just as Brandau and Plenio had originally hoped. But only probabilistically, only if you are willing to accept that some fraction of your attempts will fail completely. So the picture in 2026 is this: entanglement is irreversible under standard deterministic operations. It becomes reversible if you add a battery. It becomes reversible if you accept probabilistic failure. The irreversibility is real but not absolute. It depends on your framework, your resources, your tolerance for failure. No single statement captures the full truth. Entanglement resists simplification at every turn, and this resistance to simplification is itself the point. Because every attempt to reduce entanglement to a simple story, two particles connected across space, has failed. Every attempt to govern it with a single law, a single entropy, a single measure, has failed. Every attempt to make it behave like a well-understood classical resource has failed. Entanglement is not a thing, it is a theory. A theory with its own internal structure, its own exceptions, its own conditional laws. And that theory is, as of 2000-2006, incomplete. The open question that has haunted the field since 1998 has not been answered. And it is not a minor question. It is arguably the most important unsolved problem in quantum information theory. Here is the question: can NPT-bound entanglement exist? Remember the classification. Perez partial transpose divides entangled states into two categories: PPT states, whose partial transpose has no negative eigenvalues, and NPT states, whose partial transpose does have negative eigenvalues. The Horodeckis proved that PPT entangled states are bound, undistillable. But what about NPT entangled states? States that fail the Perez test, states whose entanglement is visible to the most powerful detection tool available. Can these states also be bound? Can there be entanglement that is detectable by partial transpose and still undistillable? If the answer is yes, the implications are enormous. It would mean that the boundary between free and bound entanglement does not coincide with the boundary between NPT and PPT. The locked region of entanglement would be larger than anyone currently suspects. States that appear, by every available test, to contain extractable entanglement would turn out to be permanently inert. The landscape of entanglement would contain hidden traps, regions that look accessible but are not. If the answer is no, if all NPT states can be distilled, then the PTT/NPT boundary is the true boundary between free and bound entanglement. The locked region is exactly the PPT region and no larger. This would be a cleaner, more elegant picture, but 27 years of effort have failed to prove it. The Horodecki family themselves highlighted this as one of the central open problems in their 2022 paper in PRX Quantum, Volume 3, Article 0101. After a quarter century of work, the people who discovered bound entanglement cannot tell you how much of the entanglement landscape is locked. They know the locked region exists. They do not know its full extent. And you should find that deeply unsettling, because entanglement is not an abstract curiosity. It is the resource at the foundation of quantum computing, quantum cryptography, quantum teleportation, and quantum sensing. Every quantum technology that has been proposed, funded, and hyped over the past 2 decades depends on the assumption that entanglement can be created, distributed, purified, and put to work. The discovery that some entanglement is permanently locked, that manipulating it is fundamentally irreversible, that it does not combine additively, and that it can die without warning, does not invalidate those technologies, but it means their foundations are far less understood than the press releases suggest. You were told entanglement is a resource. That is true, but you were not told that this resource has properties unlike any resource in classical physics. Properties that are still being discovered. Properties that physicists cannot fully characterize even after 27 years of dedicated effort. Properties that include permanent loss, discrete death, and arithmetic that violates basic addition. And now we need to talk about what all of this means when you put it together, because each of these four results, bound entanglement, non-additivity, sudden death, and irreversibility, is disturbing on its own. But the pattern they form collectively is something else entirely. There is a story the physics community tells itself about entanglement. It goes like this. Einstein, Podolsky, and Rosen raised the question in 1935. Bohr responded. Bell wrote his theorem in 1964. Clauser and Friedman tested it in 1972. Aspect closed the major loopholes in 1982. Zeilinger extended the work, and in 2022, the Nobel Committee confirmed the whole thing. Entanglement is real, the universe is not locally realistic, the story has a beginning, a middle, and an end. It is clean, it is satisfying, and it is at best chapter 1 of a much longer and much darker book. The four results we have walked through do not merely add complications to the entanglement story, they rewrite it. And the rewrite is so thorough that the word entanglement itself becomes insufficient. You cannot use the same word for the clean Bell pairs that power quantum teleportation and for the bound entangled states that the Horodecki discovered. You cannot use the same word for a resource that follows Shannon-like additivity rules and a resource where 0 plus 0 is positive. You cannot use the same word for a connection that fades gradually and one that is killed at a precise instant. You cannot use the same word for a transformation that is reversible with a battery and one that permanently destroys 41.5% of your investment without one. The word entanglement is doing too much work. It is covering phenomena so diverse and so incompatible that using a single term for all of them is almost misleading. But the physics community has not developed the language to replace it. And this is part of why these results are so poorly communicated to the public. Not because they are too complex to explain. You have followed the explanations in this video without a physics degree, but because the narrative framework does not exist, the story of entanglement that the public knows, the one with Einstein and Bell and spooky action, has a protagonist, an antagonist, a conflict, and a resolution. The story of bound entanglement, non-additivity, sudden death, and irreversibility does not have a resolution. It has an expanding frontier of strangeness with no visible boundary. Let me show you the pattern. Bound entanglement, discovered in 1998, says that entanglement can be created but not recovered. You invest resources to produce a bound entangled state. Those resources do not come back. The entanglement is real but permanently trapped. The arrow points one way. Creation without output. Non-additivity, proven in 2008 and 2009, says that the value of entanglement depends on context. A channel that is useless alone becomes useful in combination. A state that adds nothing individually contributes to a joint system that exceeds the sum of its parts. The arrow is not just one way, it is not even consistent. The rules change depending on what else is present. Entanglement sudden death, predicted in 2004 and confirmed in 2007, says that entanglement does not follow the universal pattern of decay. It does not fade asymptotically like every other known physical quantity. It is extinguished at a finite time. The arrow is not gradual, it is abrupt. A threshold, a boundary, a moment at which the connection goes from existing to not existing, with nothing in between. And irreversibility, proven in 2003, says that the arrow of entanglement manipulation points in one direction with permanent, quantifiable loss. 41.5% for the omega-3 state. There is no Carnot engine. There is no zero loss cycle. Every round of conversion between entangled states burns some of the entanglement permanently, and this burning is not a flaw in the process. What kind of physical resource behaves this way? What kind of connection can exist without being usable, combine in ways that violate arithmetic, vanish without decaying, and resist recovery with calculable permanent loss? Nothing classical, nothing in thermodynamics, nothing in Shannon's information theory, nothing in your daily experience. The closest analogy might be something like a currency that can be earned but not fully spent, whose exchange rate depends on what other currencies you hold at the time, that can be destroyed in your wallet at a moment you can calculate but not prevent, and whose conversion between denominations permanently vaporizes a fixed fraction of the total. But even that analogy fails because currencies do not exhibit superactivation, where two worthless denominations combine into a valuable one. The truth that physicists have been slowly, reluctantly, and quietly assembling over the past 27 years is this: entanglement is not a property of particles. It is a property of the relationships between particles, and that relational property has its own physics. Not metaphorical physics, actual physics, with theorems and proofs and experimental confirmations. A physics of relationships that includes its own form of irreversibility, its own form of death, its own violation of additivity, and its own permanently inaccessible regions. And here is where I need to push further, because the implications of this have not been stated clearly enough by anyone, and they should be. If entanglement is governed by its own laws that are distinct from and incompatible with thermodynamics, then the quantum world has at least two independent arrows: the thermodynamic arrow, governed by the second law, pointing toward increasing entropy, and the entanglement arrow, governed by the irreversibility that Lamy and Regula proved, pointing toward permanent loss of entanglement in manipulation. These two arrows are not the same. The thermodynamic arrow is universal and unconditional. The entanglement arrow is real, but framework-dependent. They operate on different mathematical structures. They measure different things. They cannot be reduced to each other, and the relationship between them is not understood. This is not a gap in our knowledge of the kind that will be filled by a clever graduate student next year. This is a structural feature of quantum mechanics that has resisted 27 years of effort by the best minds in the field. Two arrows, two forms of irreversibility, two sets of laws governing how the universe manages its resources, and no unifying framework that connects them. Now I want to bring the biographical threads back, because they matter here, and they matter in a way that goes beyond human interest. Asher Perez, the Holocaust survivor who studied under Nathan Rosen, who created the partial transpose criterion that made all of this possible, had a famous saying: "Quantum phenomena do not occur in a Hilbert space. They occur in a laboratory." He was making a philosophical point about the relationship between mathematics and physical reality. The Hilbert space formalism, the density matrices, the partial transposes, these are tools. The phenomena they describe happen in the real world, to real photons, in real experiments. But the four phenomena we have discussed test this principle to its limits. Bound entanglement was predicted mathematically 6 years before it was created in a laboratory. Entanglement sudden death was predicted 3 years before it was observed. Non-additivity and irreversibility are theorems, proven with mathematical certainty, whose experimental implications are still being worked out. The mathematics is running ahead of the laboratory. The formalism is discovering features of reality that experimentalists have not yet fully explored. Perez died on January 1st, 2005. He was buried beside Nathan Rosen at Sted Yehoshua Cemetery. The man who co-authored the EPR paper questioning entanglement's completeness, and the man who created the tool that revealed entanglement's deepest strangeness, lying side by side. The circle is closed with an elegance that physics rarely achieves. The Horodecki family continues to work from Gdansk. Rizard, now in his 80s, is still active. Mikkel, who also holds a master's degree in theology and plays violin alongside his sons, continues to produce foundational results. The family that discovered bound entanglement has spent 27 years mapping its consequences, and they are the first to tell you the map is incomplete. And Eberle, the giant of quantum optics who discovered that entanglement can die suddenly, taught his last class just weeks before his death in April of 2000. Over 43,000 citations. The man who showed the physics community that the most fundamental quantum connection can be severed at a calculable instant, gone at 89. These are not sidebars. These are the people who built the framework you are now sitting inside. And the framework they built, the picture of entanglement it reveals, is one that should change how you think about the quantum world at a fundamental level. You might be wondering at this point whether any of this matters outside of theoretical physics. Whether the fact that entanglement can be bound, non-additive, suddenly dead, and irreversibly lost has any consequence for the world you live in. The answer is that it does. And the consequences are arriving faster than the theory that should govern them. Quantum computing, quantum cryptography, quantum sensing, quantum networks. Every one of these technologies depends on entanglement, not casually. Quantum error correction, the process that is supposed to make large-scale quantum computers possible, works by distributing quantum information across entangled qubits. If any of those entangled connections are bound, if the entanglement is present but undistillable, the error correction fails, not gradually, completely. The bound entangled states look entangled to your diagnostic tests. They pass many entanglement witnesses, but they cannot be distilled into the clean bell pairs that error correction requires. They are imposters, real entanglement that cannot do the job of entanglement. Quantum key distribution, the cryptographic protocol that uses entanglement to create theoretically unbreakable encryption keys, depends on the assumption that entangled states can be purified and verified. The Horodecki family's own 2005 result, showing that cryptographic keys can be extracted from bound entangled states, reveals that the relationship between entanglement and security is far more complex than the standard presentations suggest. Security does not require distillable entanglement. It can emerge from the locked region. This is good news for cryptography, but deeply confusing for theory. If bound entanglement can provide security but not teleportation, not error correction, not superdense coding, then what is it for? Quantum networks, the proposed infrastructure for connecting quantum computers across distances, rely on entanglement distribution and entanglement swapping. Entangled photons sent through fiber optic cables or through the atmosphere do not merely degrade smoothly as they travel. Under certain conditions, the entanglement between them can vanish completely at a specific distance, long before the individual photons have lost their quantum properties. This is not a theoretical concern. It is a practical engineering constraint that most quantum network proposals have not adequately addressed. The distance at which entanglement dies depends on the initial state, the noise model, and the channel properties. And because of non-additivity, combining channels does not produce predictable results. You cannot simply calculate the capacity of a quantum network by adding up the capacities of its individual links. The experiments happening right now, in 2005 and 26, are beginning to probe these issues in ways that the theoretical community has been anticipating for years. In November of 2024, the CQUI experiment, the Space Entanglement and Annealing Quantum Experiment, was launched to the International Space Station It is a shoebox-sized device mounted on the exterior of the station that generates entangled photon pairs in the vacuum of space. The experiment recorded multiple Bell inequality violations with statistical confidence exceeding earlier satellite experiments, including China's Mischief satellite, which had demonstrated entanglement distribution over 1,200 kilometers in 2017. SEEK is a proof of concept for space-based quantum networks, but it is also a laboratory for studying how entanglement behaves under conditions that are impossible to replicate on Earth. Vacuum, microgravity, cosmic radiation. The degradation mechanisms are different from those in terrestrial experiments, and the possibility of observing entanglement's sudden death under these novel conditions, of measuring the exact point at which space-distributed entanglement vanishes, has been discussed in the experimental proposals. Meanwhile, in a laboratory at the University of New South Wales in Sydney, Andrea Morella's group achieved something in 2025 that connects directly to the bound entanglement problem. They demonstrated entanglement between two atomic nuclei embedded in a silicon chip, separated by approximately 20 nanometers. These are nuclear spin qubits, quantum bits encoded in the spin states of phosphorus and antimony nuclei implanted in standard silicon. The entanglement was verified and the system operates at temperatures compatible with existing semiconductor manufacturing. This matters for bound entanglement because nuclear spin systems in solid-state environments are precisely the kind of noisy decoherent systems where bound entangled states are most likely to appear naturally. The noise from the silicon lattice, the interactions with nearby electron spins, the thermal fluctuations, all of these push the entangled state toward the mixed, degraded regime where the boundary between free and bound entanglement becomes relevant. Nobody has yet observed bound entanglement appearing spontaneously in a solid-state system, but the conditions for it are present. The mixed states that emerge from nuclear spin entanglement in noisy silicon chips are exactly the kind of states where the Perez criterion becomes ambiguous, where entanglement might be present but undistillable. Detecting this would require entanglement witnesses specifically designed for bound states, a measurement technology that is only now becoming experimentally feasible. And at the Technion in Haifa, Asher Perez's own institution, researchers discovered in 2025 a new form of entanglement in photons confined to nanoscale structures. They found entanglement between different components of the total angular momentum of light, orbital angular momentum, and spin angular momentum, in regimes where classical optics would predict no such correlation. This is a new type of entanglement, not between spatially separated particles, but between different degrees of freedom of the same photon, occurring in structures smaller than the wavelength of light. Published in Nature, it represents an expansion of the entanglement concept into domains that the founders of the field never anticipated. The quantum world keeps finding new ways to be entangled, and each new way brings with it the question of whether the entanglement is free or bound, whether it is distillable or locked, whether it will fade smoothly or die suddenly, and whether manipulating it will cost more than it returns. There is another frontier that deserves discussion here because it connects the strange properties of entanglement to the deepest questions in physics. It involves gravity. In 2013, Juan Maldacena and Leonard Susskind proposed a conjecture that has consumed a generation of theoretical physicists. They called it ER equals EPR. The claim is that quantum entanglement, the EPR correlations named after Einstein, Podolsky, and Rosen, is physically equivalent to Einstein-Rosen bridges, the wormholes of general relativity. Every pair of entangled particles is connected by a tiny wormhole. Every wormhole is an entanglement. The two phenomena, one from quantum mechanics and one from general relativity, are the same phenomenon seen from different angles. If this conjecture is correct, and it remains unproven but widely discussed, then the strange properties of entanglement, are not just features of quantum information theory. They are features of space-time itself. Bound entanglement would correspond to wormholes that exist but cannot be traversed, connections in space-time that are real but permanently inaccessible. Entanglement sudden death would correspond to wormholes that collapse at specific calculable moments. Irreversibility of entanglement would correspond to irreversibility in the geometry of space-time. The arrow of entanglement would be a geometric arrow, a structural feature of how space and time are woven together at the quantum level. This is speculative. Nobody has proven ER equals EPR, but the conjecture has generated an enormous body of theoretical work, and it is taken seriously by the leading figures in both quantum gravity and quantum information theory. Maldacena is one of the most cited physicists alive. Susskind essentially founded the field of string theory phenomenology. When they propose that entanglement is space-time, the physics community pays attention. And if they are right, then everything we have discussed in this video, bound entanglement, non-additivity, sudden death, irreversibility, is not just about quantum information, it is about the fabric of the universe. The locked regions of entanglement are locked regions of geometry. The sudden death of entanglement is the sudden collapse of spatial connections. The irreversibility of entanglement manipulation is the irreversibility of geometric change. The universe does not merely contain entanglement, it is built from it, and the laws governing that entanglement, the laws we have been walking through for the past 90 minutes, are the building code of reality itself. But I want to be careful here, and I want to model the kind of honesty that this topic demands. ER equals EPR is a conjecture. It has not been proven. It may never be proven in the form Maldacena and Susskind stated it. The connection between entanglement and geometry is real and mathematically rigorous in certain specific contexts, particularly in the ADS/CFT correspondence, where entanglement, entropy in the boundary theory equals the area of minimal surfaces in the bulk spacetime, a result proven by Ryu and Takayanagi in 2006 and made rigorous by Lukovic and Maldacena in 2013. But extending this to arbitrary quantum systems outside the ADS/CFT context is an open problem. What is not speculative is the impact. Regardless of whether ER equals EPR turns out to be exactly correct, the properties of entanglement we have discussed constrain any future theory of quantum gravity. Any theory that explains how space-time emerges from quantum mechanics must account for the fact that the quantum correlations underlying that emergence can be bound, non-additive, suddenly dead, and irreversible. These are not optional features, they are proven properties of entanglement. Any theory of quantum gravity that cannot accommodate them is wrong. And no current theory of quantum gravity fully accommodates them. The bound entanglement problem, the non-additivity problem, the irreversibility proof, none of these have been fully integrated into the leading approaches to quantum gravity. They are known, they are cited, but their implications for the geometry of space-time have not been worked out. The field is aware of them and has not yet figured out what to do with them. This is the invisible scandal that has been building throughout this entire story. Not a scandal of suppression or conspiracy, a scandal of omission. The properties of entanglement that we have discussed are published in the most prestigious physics journals in the world. They are cited thousands of times. They are known to every active researcher in quantum information theory, and yet they are almost completely absent from public discourse about quantum mechanics. When the 2022 Nobel Prize was awarded for entanglement experiments, the announcement described entanglement as the phenomenon where two particles behave like a single unit, even when they are separated. That description is not wrong, but it is so incomplete that it borders on misleading. It is like describing fire as a warm thing and stopping there. Yes, fire is warm, but it also burns. it also spreads. It also consumes its fuel irreversibly. And if you only tell people about the warmth, they will be completely unprepared for what fire actually does. The public has been told about the warmth of entanglement, the spooky connection, the instantaneous correlation, the Nobel Prize. What the public has not been told is that entanglement burns, that it locks, that it dies, that it refuses to be fully recovered, and that the people who understand these properties best cannot fully explain them, even to each other. The 2022 Nobel Prize in Physics honored work from the 1970s and 80s. Clauser's experiments were in 1972. Aspects were in 1982. Zeilinger's contributions span the 1990s and 2000s. The prize recognized a generation of work confirming that entanglement is non-local, that Bell inequalities are violated, that the universe is not locally realistic. This is important. This is foundational, but it is the beginning of the story, not the end. The discoveries we have discussed, bound entanglement in 1998, sudden death in 2004, non-additivity in 2008, irreversibility in 2003, represent the next generation of entanglement science. They are the results that come after the Nobel, after the confirmation that entanglement is real. When the question shifts from, is it real, to what are its actual properties? And the answer to that second question is far more disturbing than the answer to the first. Non-locality is strange. The idea that measuring a particle here instantaneously affects a particle there violates your intuitions about locality and independence. But non-locality is at least conceptually simple. Two things are connected. The connection is instantaneous. Done. Bound entanglement is not conceptually simple. A connection that exists but cannot be used. A resource that is verified but inaccessible. A property that is provably present and permanently inert. This requires a new category of thought, and it requires accepting that the quantum world contains phenomena that have no analog in any domain of human experience. Non-additivity is not conceptually simple. Two zeros making a positive. Two useless things combining to become useful. This is not strange in the way that spooky action is strange. It is strange in a deeper way. It means the value of a quantum resource is not determined by the resource itself, but by the context in which it exists. There is no intrinsic value, there is only relational value, and the relations are non-linear, non-additive, and computationally intractable to determine. Sudden death is not conceptually simple. A connection that does not decay, but terminates. This is not like anything in your experience of the physical world. Everything you have ever watched decay, from radioactive atoms to the foam on a beer, decays gradually, asymptotically, approaching zero without reaching it. Entanglement reaches zero, exactly zero, at a calculable instant, while the components themselves persist unchanged. And irreversibility is not conceptually simple. A transformation that permanently destroys a quantifiable fraction of the resource, not because of noise or imperfection, but because of the mathematical structure of quantum mechanics. 41.5% for one state, different fractions for different states, but always positive, always permanent, always a one-way loss. These four properties, taken together, describe something that is unprecedented in the history of physics, a resource that is simultaneously real and inaccessible, context-dependent and quantifiable, discretely fragile and mathematically precise, and irreversibly degraded under manipulation. There is no classical analog. There is no thermodynamic analog. There is no information theoretic analog. Entanglement is in a category of its own, and the fact that this category exists, that nature contains a resource with these properties, is something that should be front-page news, and is not. And there is a temporal pattern here that deserves your attention because it reveals something about how physics actually progresses, versus how the public is told physics progresses. The public narrative of entanglement follows a clean chronological arc. 1935, EPR paper, the question is raised. 1964, Bell's theorem, the question is made testable. 1972 through 1982, Clauser and Aspect, the tests are performed. 2022, the Nobel Prize, the story is completed. Each step builds on the last. Each result is communicated to the public. The arc is satisfying. It has a beginning, a middle, and an end. But the real history of entanglement theory over the past 30 years follows a completely different pattern. It is not a clean arc. It is a cascade of increasingly strange discoveries, each one undermining the previous generation's assumptions, each one published to great excitement within the specialist community and near total silence outside it. 1996, Perez publishes the partial transpose criterion, a new tool for detecting entanglement, not communicated to the public. 1996 through 97. The Horodecki family extends the criterion and shows it is both necessary and sufficient for small systems. 1998, bound entanglement is discovered, published in Physical Review Letters. Over 800 citations and growing, not communicated to the public. 1999, bound entanglement activation is predicted, the dead resource that helps the living, not communicated to the public. 2004, entanglement sudden death is predicted, published in Physical Review Letters. Over 1,200 citations, not communicated to the public. 2005, cryptographic keys extracted from bound entanglement, published in Physical Review Letters, not communicated to the public. 2007, entanglement sudden death confirmed experimentally, published in Science, not communicated to the public. 2008, 0 plus 0 equals positive for quantum channels, published in Science, not communicated to the public. 2009, the additivity conjecture is disproved, published in Nature Physics, not communicated to the public. 2009, bound entanglement created in the laboratory, published in Nature Physics, not communicated to the public. 2014, Perez's own conjecture about bound entanglement and Bell violations is disproved, published in Nature Communications, not communicated to the public. 2023, entanglement irreversibility is proven, published in Nature Physics, not communicated to the public. 2023, the Brandau-Plenio proof is found to contain a fatal gap, published in the journal Quantum, not communicated to the public. 25 years of results, hundreds of papers, thousands of citations, published in the most prestigious journals in physics, and outside the specialist community, near total silence. This is not a conspiracy. There is no gatekeeping. The papers are public. The ArcSieve preprints are freely available. Anyone can read them. The silence is structural. It exists because the public narrative of entanglement was set decades ago, and these results do not fit into that narrative. They cannot be added as footnotes to the spooky action at a distance story. They require a completely new story. And nobody has written that story. The science communicators have not written it because the results are technically demanding and do not reduce to simple analogies. The physicists have not written it because they are still working on it, still trying to understand what the results collectively mean. And the funding agencies and the quantum technology companies have not encouraged it because these results complicate the narrative that quantum technology is well understood and ready for deployment. So the results sit in the journals, cited by specialists, ignored by everyone else. And the gap between what the public thinks entanglement is and what entanglement actually is grows wider every year. I want to be precise about what I am not saying. I am not saying that quantum technology is a fraud. Quantum computers work. Quantum key distribution works. Quantum sensing works. The entanglement that powers these technologies is real, and the engineering that manipulates it is sound, within its demonstrated domain of operation. What I am saying is that the theoretical foundation of these technologies has properties that are not accounted for in most engineering analysis. Properties that could impose fundamental limits on scaling, on network capacity, on error correction overhead, on the distance over which entanglement can be distributed. Properties that have been rigorously proven and experimentally confirmed, and that the engineering community is only beginning to engage with. The gap between theory and engineering in quantum technology is not unusual. Classical technologies have similar gaps. Nobody fully understood turbulence when they built the first airplanes. Nobody fully understood semiconductor physics when they built the first transistors. Technology can and does outrun theory. But the specific properties of entanglement that we have discussed, the lockdown, the non-additivity, the sudden death, the irreversibility are not minor corrections to the standard picture. They are fundamental features of the resource that the entire quantum technology enterprise depends on, and they are, as of 2026, imperfectly understood, imperfectly characterized, and imperfectly integrated into the engineering frameworks that are supposed to govern the development of quantum technology. This matters. It matters because the investments being made in quantum technology are enormous. It matters because the promises being made to governments and investors and the public are based on a picture of entanglement that is at best incomplete. And it matters because the open questions, particularly the NPT-bound entanglement question, could reveal that the limitations are more severe than currently assumed. Nobody is lying. Nobody is hiding results. But the full picture is not being communicated, and the full picture is far stranger, far more constrained, and far less reassuring than the version you have been given. Let me take you deeper, because there is a level beneath the individual results, beneath the bound states and the non-additivity and the sudden death and the irreversibility, where the implications become genuinely difficult to confront. Entanglement was supposed to be the bridge between quantum mechanics and the classical world, the bridge between information and physics, the bridge, perhaps, between quantum mechanics and gravity. Every major research program in foundational physics over the past 3 decades has placed entanglement at its center. Quantum error correction, which makes quantum computing possible, is built on entanglement. The holographic principle, which suggests that the information content of a region of space is proportional to its surface area rather than its volume, is expressed through entanglement entropy, the ADS/CFT correspondence. The most important theoretical development in high-energy physics in the past 30 years relates the entanglement structure of a quantum field theory to the geometry of a higher dimensional space-time. Entanglement is not a feature of these programs, it is their foundation. And the foundation has properties that nobody anticipated and nobody fully understands. Consider what it means for quantum error correction, that entanglement is irreversible. Quantum error correction works by encoding a logical qubit, the qubit you actually want to protect, across many physical qubits using entanglement. When errors occur, you measure certain properties of the physical qubits, detect which errors happened, and correct them. The process requires creating entanglement, consuming it to detect errors, and replenishing it for the next round. Every round of error correction is a round of entanglement manipulation, and Lamy and Regular proved that every round of entanglement manipulation permanently loses some entanglement. Not much. Perhaps. The 41.5% figure applies to a specific 2-qubit state, not to the bell pairs typically used in error correction. But the principle is general. Irreversibility applies broadly, and its quantitative impact on the overhead required for large-scale quantum error correction has not been fully calculated. This is not a theoretical luxury. Quantum computing companies are betting billions of dollars on the assumption that error correction can be made to work at scale. If the irreversibility of entanglement imposes a fundamental overhead on error correction, an overhead that grows with the number of correction cycles, the implications for the feasibility and cost of large-scale quantum computing could be significant. Nobody has done this calculation, not because it is unimportant, but because the tools required, the tempered negativity and related measures that Lamy and Regular developed, are too new to have been fully integrated into the quantum computing literature. Consider what it means for quantum networks that entanglement is non-additive. A quantum network distributes entanglement between nodes, much like the classical internet distributes data. In a classical network, the capacity of a path through the network is determined by the bottleneck, the weakest link in the chain. In a quantum network, this is not necessarily true. Because of non-additivity, the quantum capacity of a chain of channels is not simply determined by the individual channel capacities. Two channels in sequence might have a combined capacity that is higher or lower than naive calculation would predict. Two parallel paths through a network might have a combined capacity that exceeds the sum of their individual capacities. Or they might not. It depends on the specific channels, the specific states, the specific protocol. There is no general formula. This means that optimizing a quantum network, deciding which paths to use, how to route entanglement, where to place repeaters, is not just a difficult engineering problem. It may be a computationally intractable one. The lack of a single-letter capacity formula, the consequence of non-additivity that Hastings proved in 2009, extends to the network setting. You cannot compute the capacity of a quantum network link by measuring the link. You would need to optimize over infinitely many uses, considering all possible entangled input states across all possible numbers of channel uses. This is not a practical limitation that can be overcome with better computers. It is a fundamental limitation rooted in the structure of quantum information itself. Consider what it means for quantum repeaters that entanglement can die suddenly. Quantum repeaters are the proposed solution to the distance limitation of quantum communication. Entanglement distributed through optical fiber degrades with distance. Repeaters break the long link into shorter segments, create entanglement across each segment, and then connect the segments through entanglement swapping. The standard analysis assumes that entanglement degrades smoothly with distance and channel loss. Entanglement's sudden death means this assumption can fail. For certain initial states and certain noise models, the entanglement does not degrade smoothly. It vanishes completely at a specific distance. If a repeater segment is longer than the sudden death distance for the states being used, the entanglement arrives dead. Not degraded. Dead. And no amount of distillation at the repeater station can recover it, because there is nothing to distill. The entanglement is not weak. It is zero. Repeater designs must account for this. Most current proposals do not, because they assume exponential decay of entanglement with distance, which is the standard model borrowed from classical signal attenuation. Entanglement sudden death means that for some configurations there is a hard distance limit, not a soft one, and that limit depends on the initial state in a way that exponential models do not capture. These are not abstract concerns. They are engineering constraints for technologies that governments and corporations are spending billions of dollars to develop. And the theoretical results that define these constraints, bound entanglement, non-additivity, sudden death, irreversibility, are not part of the standard toolkit that quantum engineers are trained with. They are known in the quantum information theory community. They are largely unknown in the quantum engineering community. The gap between the theorists who proved these results and the engineers who are building the technology that depends on entanglement is wide, and it is not closing quickly. But I want to go deeper still. because there is a philosophical dimension to these results that even the theorists tend to avoid discussing publicly, and it concerns the nature of reality itself. Quantum mechanics, as it is currently formulated, treats entanglement as a feature of the quantum state. The state of two particles can be entangled. The state evolves according to the Schrödinger equation, or its density matrix generalization, the Lindblad equation, when decoherence is included. Entanglement is something the state has. It is a property, like energy or momentum. But the four results we have discussed suggest something more unsettling. Entanglement does not merely exist as a property of states. It is managed, regulated, constrained by rules that have no analogue in the management of any other physical quantity. Energy is conserved, momentum is conserved, charge is conserved. These conservation laws are clean, universal, and unconditional. Entropy increases, but this increase is statistical, emergent from the microscopic dynamics of many particles. And entropy increase is in principle reversible for isolated subsystems. The second law of thermodynamics is a tendency, not an absolute prohibition. Fluctuations can temporarily decrease entropy. The laws governing energy and entropy are well understood, universal, and conceptually straightforward. The laws governing entanglement are none of these things. Entanglement is not conserved. It can be created and destroyed, but the creation and destruction follow rules that are unlike any conservation law. Entanglement can be created at a cost, but that cost cannot always be recovered. Bound entanglement represents a permanent investment with no return. Entanglement can be destroyed, but the destruction is not smooth. It can be abrupt, at a calculable instant, in a way that violates the exponential decay pattern followed by every other known quantity. Entanglement can be combined, but the combination does not follow additive rules. Two zero-value resources can combine to positive value, and entanglement manipulation is irreversible with a quantifiable, state-dependent fraction permanently lost in each cycle. These are not the laws of a passive property. These are the laws of something that is actively regulated, something the universe keeps track of, something it manages, not in a conscious, intentional sense, but in the sense that the mathematical structure of quantum mechanics includes specific, precise mechanisms for creating, locking, killing, and permanently degrading this one particular type of correlation, mechanisms that have no parallel for any other physical quantity. When the Horodeckis discovered bound entanglement, they discovered that the universe has a mechanism for permanently locking quantum correlations. When Yu and Eberle discovered sudden death, they discovered that the universe has a mechanism for discretely terminating quantum correlations. When Lamy and Regular proved irreversibility, they proved that the universe has a mechanism for permanently destroying quantum correlations during manipulation. These are not accidents of the formalism. They are structural features of quantum mechanics. They would appear in any mathematically equivalent formulation of the theory. They are telling us something about what the universe does with quantum correlations, and what it does is far more complex, far more structured, and far more controlling than what it does with any other physical resource. Think about that for a moment. The universe does not have special mechanisms for managing energy. Energy is conserved by symmetry, by Noether's theorem, as a consequence of time translation invariance. It is passive, automatic. The universe does not have special mechanisms for managing momentum or charge. These are conserved by spatial translation and gauge symmetry, respectively. Again, passive, automatic, but entanglement has specific active asymmetric management rules. Creation is allowed, but comes at a cost. Recovery is forbidden beyond a certain point. Destruction can be abrupt and total. Combination is non-additive. Manipulation is irreversible. These rules are not consequences of any known symmetry. They are not derivable from any simple principle. They emerge from the mathematical structure of quantum mechanics in ways that are still being catalogued and are not fully understood. If you wanted to design a universe that actively regulates quantum correlations, that imposes limits on what those correlations can do, that maintains locked regions and death thresholds and irreversible losses, you would design rules that look very much like the ones the Horodeckis, Yu and Eberle, Smith and Yard, Hastings and Lamy and Regular have discovered. The question of why the universe has these rules, what purpose they serve, what deeper principle they reflect, is unanswered. It may be unanswerable with current physics, but the rules themselves are not in question. They are proven. There is one more thing I need to tell you, and it is the thing I have been building toward since the beginning. In 2018, a physicist named Matteo Fadel, working at the University of Basel in Switzerland, published the results of an experiment that had been decades in the making. His team created entanglement between clouds of approximately 500 atoms each, not between individual particles, between macroscopic, visible collections of atoms. The entanglement was verified using spin correlations, and the result was published in Science. It was hailed as a step toward testing whether quantum mechanics applies at scales visible to the naked eye. In 2021, a group at the Delft University of Technology in the Netherlands, led by Romuald Hansen, demonstrated entanglement between 3 quantum network nodes separated by distances of over 1 kilometer. The entanglement was distributed, stored, and verified across a small quantum network in a real urban environment. Published in Nature, it was called the first multi-node quantum network. In 2204, Chinese researchers established a quantum link between their Jinan, 1 microsatellite, and ground stations in both China and South Africa, distributing entanglement across 12,900 kilometers, the longest entanglement distribution ever achieved. In each of these experiments, entanglement was created, distributed, and measured. In each of them, the standard narrative applies. Particles are connected, measurements correlate. Quantum mechanics works, but in every one of these systems, the bound entanglement question is lurking. At every stage of distribution and manipulation, some fraction of the entanglement may be crossing into the bound region, becoming permanently locked. The irreversibility proven by Lamy and Regular means that every round of entanglement swapping, every manipulation required to connect network nodes, every purification step in the distribution chain permanently destroys some entanglement. The sudden death threshold means that under certain noise conditions, the entanglement will not merely degrade, but vanish entirely at a specific point in the chain. And the non-additivity means that combining network links does not produce predictable capacities. These experiments work, the entanglement is real, the correlations are measured, but the full picture of what is happening to the entanglement during these processes, how much is being locked, how much is being irreversibly lost, where the sudden death thresholds lie, is not known. The experiments are running ahead of the theory, which is running ahead of the public understanding, which is still stuck on spooky action at a distance. And this brings me back to Asher Perez, because Perez understood something about quantum mechanics that almost nobody, including many physicists, fully appreciates. He understood that the formalism is not the physics. The density matrices and partial transposes and Hilbert spaces are mathematical tools. They are extraordinarily powerful tools that have predicted every experimental result with perfect accuracy for a century. But they are descriptions, not explanations. They tell you what happens. They do not tell you why. The 4 properties of entanglement we have discussed, bound entanglement, non-additivity, sudden death, and irreversibility, are predictions of the formalism. They are derived from the mathematics of quantum mechanics using rigorous proof techniques. They are confirmed where experiments exist. by those experiments. They are as well established as any result in physics. But the formalism does not explain them. It does not tell you why the universe contains a permanently locked region of quantum correlations. It does not tell you why two zero capacity channels can combine to positive capacity. It does not tell you why entanglement death is discrete rather than continuous. It does not tell you why manipulation is irreversible with a specific calculable loss. These properties emerge from the equations, but the equations do not illuminate their origin. And this is the deepest form of the abdication of authority that has been running through this entire story. The physicists who discovered these results can tell you that they are true. They can prove it with mathematical certainty. They can confirm it with experimental data. What they cannot tell you is what it means. Not in the technical sense. The technical meaning is clear. But in the foundational sense, what does it mean that the universe manages entanglement the way it does? What principle, what law, what feature of reality requires that quantum correlations be locked, killed, non-additive, and irreversibly degraded? Why these rules are not simpler ones? The honest answer is that nobody knows. Not the Horodeckis, not Lamian Regula, not the Nobel laureates, not the quantum gravity theorists. Nobody. The rules have been discovered, the principles behind them have not. And the open question that makes this ignorance most acute, the one that has resisted every attempt at resolution for 27 years, is the one I mentioned earlier. Can NPT-bound entanglement exist? Let me explain why this question matters so much that it keeps quantum information theorists awake at night. If NPT-bound entanglement does not exist, if every state with a negative partial transpose can be distilled, then the bound region is exactly the PPT region. It is a known, characterized set. It is strange, but it is mapped. The territory, while unusual, has defined borders. But if NPT-bound entanglement does exist, if there are states that fail the Perez test, states whose entanglement is visible and detectable, then the bound region extends beyond the PPT boundary. The locked territory is larger than the map shows. There are traps in the entanglement landscape that no current test can identify. States that appear to contain usable entanglement but do not. States that would fool your diagnostic tools into reporting extractable correlations that are in fact permanently inaccessible. This would mean that the problem is not just that some entanglement is locked. It would mean that you cannot always tell which entanglement is locked. The bound region would have invisible extensions, regions that look free but are not, regions where the entanglement responds to your tests as if it were distillable but is not. And the question of where these invisible extensions are, how large they are, what states they contain, would join the list of things that the formalism predicts but cannot practically determine. 27 years. Every major group in quantum information theory has worked on this problem at some point. The Horodeckis, Terhal, De Vincenzo, Shaw, Smolin, Bennett, Wouters, Plenio, Vedral. The leading figures of the field, spanning 3 decades, have tried and failed to resolve it. The question remains open. The locked region of entanglement may be exactly what we think it is, or it may be larger, possibly much larger. We do not know. And here is the final implication, the one that has been approaching since the first paragraph, and that I cannot soften or qualify. You live in a universe where the most fundamental connections between objects, the quantum correlations that underlie all of matter and possibly space-time itself, are subject to rules that include permanent lockdown, discrete death, non-additive arithmetic, and irreversible loss. These rules were not anticipated by the founders of quantum mechanics. They were discovered, one by one, over 27 years by mathematicians and physicists working in Gdansk and Rochester and Amsterdam and Tokyo, published in the highest impact journals in science, and largely ignored by the public and the popular science establishment. The 2022 Nobel Prize in Physics celebrated the confirmation that entanglement is real. It did not mention that entanglement has properties that make it unlike any other known physical phenomenon. It did not mention that those properties have been proven and published over the course of a quarter century. It did not mention that the most basic question about those properties, the extent of the locked region, remains unanswered. Asher Perez, buried beside Nathan Rosen in Haifa, created the mathematical tool that revealed these properties. The Horodecki family, working from Gdansk for a quarter century, discovered that entanglement has a permanently locked region and spent their careers mapping its boundaries. Joseph Henry Eberle, who arrived at quantum optics through a question about submarine lasers and stayed for 60 years, showed that entanglement can be killed at a calculable instant. Ludovico Lamy and Bartosz Regula, two researchers in their early 30s, proved that the universe permanently destroys entanglement during every manipulation, with no possibility of full recovery. Graham Smith and John Yard proved that two worthless quantum channels can combine into a useful one. Matthew Hastings proved there is no simple formula for quantum capacity. And Peter Shaw, whose unification theorem ensured that all the additivity conjectures would die together, went on to win the Turing Award. These are the people who mapped the territory. And the territory they mapped is one where the fundamental connections underlying reality are governed by rules that physicists cannot fully explain, that engineers have not fully incorporated, that the public has not been told about, and that the theorists themselves describe with a mixture of precision and bewilderment. The property that should not exist is not one thing. It is all of them. Bound entanglement should not exist in a universe where entanglement is a usable resource. Non-additivity should not exist in a universe where resources combine additively. Sudden death should not exist in a universe where decay is exponential. Irreversibility should not exist in a universe where the fundamental laws are time reversible. Each of these properties should not exist. Each of them does. And the fact that they coexist, that the same physical phenomenon simultaneously displays all four of these impossible properties, is something that the physics community has known about for years and has not known what to say about. The scientists did not go quiet because they were hiding something. They went quiet because they found something they could prove but not explain, something they could publish but not narrate, something that is true and well established and rigorously confirmed and does not fit into any story that the public or the physics community currently knows how to tell. Entanglement is real. The Nobel Committee was right about that. But entanglement is also locked, non-additive, discretely mortal, and irreversibly degraded. And the fact that the same word, entanglement, covers both the clean correlations that Einstein worried about and the bound, dying, irreversible resource that the Horodeckis discovered, is itself a kind of silence, a refusal to distinguish between the entanglement of the textbooks and the entanglement of the theorems, a refusal that keeps the public picture simple and keeps the real picture hidden. The locked region may be larger than anyone suspects. The sudden death thresholds may be closer than anyone has measured. The irreversible losses may accumulate faster than anyone has calculated. And the open question, the 27-year-old question that nobody can answer, may turn out to reveal that the territory we have not mapped is vaster than the territory we have. That is not speculation. That is the state of knowledge. That is what the data and the proofs and the experiments and the open problems collectively say. Entanglement is the foundation of quantum technology and possibly of space-time itself. And the people who understand it best will tell you if you ask them directly, and they are being honest, that they do not fully understand it, that the properties it has should not exist, that the rules it follows have no known origin, and that after 27 years, the question of how much of entanglement is permanently irrevocably locked away from all possible use remains open. The universe built itself out of quantum correlations, and then it locked some of those correlations away, killed others at precise moments, refused to let the rest be fully recovered, and arranged the entire system so that the rules of combination violate basic arithmetic. And nobody can tell you why.